Hi guys, in this video we're going to talk about nuclear reaction equations. Hopefully you've already watched the video about nuclear chemistry, an introduction to nuclear chemistry. This is how we are going to be writing the reactions that take place. So we're going to switch over to some Cornell paper. And I already wrote down the objective and our essential question. You'll want to fill out your name and date. We're talking about nuclear reactions, and our essential question is, how do you write and balance a nuclear reaction equation? So we're going to start by reviewing a little bit about nuclear reaction equations and what the difference is between a nuclear equation and a chemical equation. First off, they look similar. They look like chemical equations. The chemical equations, though, the difference is they have chemical equations have compounds, and when you balance them, you're making sure you have the same number of atoms on each side of the arrow. And in a nuclear reaction equation, instead of looking at compounds, you're looking at atoms, and instead of making sure you have the same number of atoms, what you're looking for is that you have the same mass number and atomic number. And I'll explain what I mean by that. That these two things right here, that is about balancing. So we always balance. Why do we balance? To show the conservation of mass. So let's look at a couple of examples here of just what a nuclear reaction equation looks like. We've seen some examples already, and these are going to be the same examples that we wrote down before. So here's an example of alpha decay. Alpha decay looks like this. Let's say we have polonium-210 with a atomic number of 84. That decays via alpha decay into this other stuff called lead, spitting off an alpha particle. Now we could have easily written the He for an alpha particle also. And in that case, the equation would look exactly the same, but instead of this alpha here, there would be the letters He. Now for gamma decay, remember, is where an electron comes out of the nucleus and a neutron turns into a proton. And an example that does that is that tritium, that hydrogen-3, it turns into helium when it does this. And so we end up with an equation that looks like that. What I was talking about up here with the balancing thing, notice how the 210, that's the same as 206 plus 4, and 84 is the same thing as 82 plus 2. Same thing here, 3 is the same as 3 plus 0, and 1 is the same as 2 minus 1, so we're just making sure that the math works out there. For, whoops, that's not gamma, that's beta. My bad. Gamma decay is the one that looks weird. We won't see a lot of those after right now. Remember that we just have the little star on it, and when it gives off a gamma particle, which is really a photon, a chunk of light, nothing happens except the star goes away. So that's all that one looks like. So when we are looking at these equations, you're going to be asked to fill in some blanks on some of these. So let's talk about how to balance them. How to balance. Okay, so we'll call this the mass number here. When you have the mass numbers, your arrows, the sum over here has to be the same as the sum over here. You just have to make sure that works out correctly. And then the same thing with the atomic number. The sum of the atomic numbers over here has to equal the sum of the atomic numbers over here. So that's pretty easy. So let's take a look at this. We might also need our handy periodic table. Unless you've got a whole lot of atomic numbers memorized, you're definitely going to want a periodic table. So let's do a few examples, maybe like 2. So in this first example, we'll have iodine 129. Iodine's atomic number is 53, and that's going to go through this reaction here, and the question might look like this with a blank right there, and maybe it has a little blank here and a little blank here. So we've got to figure out what's going on. First off, this tells you that it's beta decay, in case you needed to know. This is beta decay. And so we've got to figure out what iodine is going to turn into. So my numbers have to add up. So I've got 0 plus something has to equal 129. So this has got to be a 129. And then 53 has to be something minus 1. Well, minus 1 makes this go up to 54, so I put a 54 there. Now to figure out what letters go here, the bottom number identifies the element. That might be a useful thing to write down. So 54 is what I have to look up in the periodic table. Here's my handy periodic table. There's 54, so this is xenon. So I'm going to write Xe. Seems pretty easy to me. Maybe it's not so easy to you. Okay, so let's try a harder one. And let's do this one right here. So this is 255, and there's a blank right here, and it says RF. And then it's got a 4 and a 2 and a little alpha, and then it's got a big blank here with a little blank and a little blank. Okay, so now we've got to figure this one out. So RF, that's Rutherfordium, I think. Rutherfordium? Yeah. That is on the periodic table somewhere, so we've got to find it so we can figure out what that number is down there. So here's RF right there. RF's number is 104, so I'm going to put 104 right down here. That bottom number is the atomic number. So when I'm trying to figure out what goes over here, I just need to do my math. So 255 is 4 plus something. Well, that would be 251. And 104 is 2 plus something, so that would be 102. Now to figure out the letters, I just have to look that up in the periodic table. 102, where's 102? There's 102, right there. Nobelium, so I'm going to write NO. This one, in case you didn't notice, was alpha decay. Now there's other kind of chemical or nuclear reactions that we could write down here. Here, we'll do this nice difficult one. Sometimes they either decay more than once, or some interesting things happen when they break down. So we're going to let's do this one. So we've got 85 Br, and that's going to give us something with our two little blanks here, plus 85 Kr, and a blank right here. There's a blank on that Br too. And then it's giving off a gamma. Gamma often comes with something else, so let's see if we can't figure out what's going to be here. All right, so first off, my 85 and my 85 is all I have over here, so there must be a 0 here because it's got to be 85 on this side and 85 on that side. So again, this is where your equal sign is. In order to figure out the atomic numbers, I got to look up Kr and Br. They're both on this side. Oh, they're right next to each other. So Br is right here. Can you see Br right there? It's a 35. And krypton is a 36. So it looks like I've got to have 35 on this side, and I've got 36 over here, so I need a -1. So that, a 0 and a -1, is a beta particle. So this is undergoing both beta and gamma decay at the same time. So that's what those reaction equations might look like. Now, what if you were doing something else where your particles were, say, breaking down? Through this process you'll talk about later called fusion or fission. Fusion is when they come together, fission is when they break apart. What happens when you have a particle that looks like that? Well, it works exactly the same way. I'm trying to find a good example here. These examples are not very good, though. Sometimes when they break apart, we end up doing the same thing, but with different... No, I don't like this example either. Well, maybe we won't look at an example. Sometimes I'll come up with an example here. So let's say we have thorium, TH, which is atomic number 90, and maybe it's 231. Who knows? And let's say that breaks roughly, or maybe it breaks into a couple of pieces, and one of them is tellurium 127. And we need to figure out what the other thing is and what its numbers are too. And we also need a number here. So This would be an example of what we'll talk about later. This is fission. So when we've got thorium, thorium's over here, tellurium is somewhere in the middle. Where did tellurium go? Te, where are you? Wow, I lost it. There it is, tellurium. Tellurium is 52, so we'll put a 52 there. So to figure out what goes here, I just have to figure out what numbers might add together. So 90, if I write this down, 90 equals 52 plus something. So what I have to do is subtract that 52 from 90. 52 from 90, let's see, that's whoops, that's an 8, carry the 1, it's a 38, I think. Does that add up? 38? That doesn't seem right. Yeah, that adds up, 38. So 38 would go right there. And then to figure out the number that goes on top, I know that 231 has to equal 127 plus something. So I'll take 231 minus 127. Let's see here. That would be a 4 and a 0 and a 1. So 104. So then to figure out what letters go there, I just have to figure out what element 38 is. Here's my handy periodic table. There's the 38 right there. It's strontium, Sr. So that would be the two pieces that it ends up being. So those are just some examples of what nuclear reactions look like and how you figure things out. Remember that you're just trying to make the math work out correctly so that you can get the right answer. Thanks for watching.